Data communication. So mainly, what will happen in data communication? So you can see there will be a transmitter section, okay, which generates any message signal and it transmits through the antenna to the receiver section, which receives here. Okay, so this is TX and this is RX. Okay, let's say the message signal which generated here, which want to receive by the receiver section, some of them get error. Okay, so that the message which actually transmitted to the receiver may not be get exact information, it has some erroneous output. So in order to make the make understand how the error has been come and how to detect that error, and is it possible any error correction in the receiver section or not, we are going to see all these things. Before that, I'm going to start one important thing which is actually called parity circuits. So parity circuit is nothing else, it's again a combination logic circuit. We are going to see that in brief today. So in parity circuit, what it will do, it only detects the errors. Okay, so parity circuits are nothing else, it only detects the error, it only tell whether there is a error or not, it only detects the errors. That too, it has bound thing. What is the bound thing? Only one bit error, one bit error. If there is a 1 bit error in the message signal, this parity circuit will detect and say to the user or the receiver section, yeah, there is a error in your transmitted signal, so need to be rectified before sending. So do you all understand? Only it detects the errors. The parity circuit only detects the error. Okay, so before that, what it would be done, so see here, it would have a parity generator circuit. Okay, so I'm going to tell one by one. So this is parity generator, PG, parity generator circuit. Let's say n bit message signal has been come over here, n bit message. Okay, so you can also say data also, n bit message or data. Okay, so it actually generates a parity bit depending upon this n bit message signal. Okay, so it actually, what it will do, it will actually generates a parity bit. Please try to understand, very important thing. You have not seen all these things earlier anywhere, so please try to understand. If you are not understanding, please let me know. Okay, next what happened, this parity generator generates this parity bit where actually in the transmitter section, and it transmits to the receiver. Okay, so in the receiver, what it will do, there will be a error detecting circuit, error detecting circuit. There will be error detecting circuit. This whatever data they have got here, please try to understand, including the parity bit. Please try to understand, including this parity bit, this n bit data, including this parity bit, whatever they have achieved at the receiver section, it actually tells whether it has a error or not. If it is having error, it provides error equal to 1. If it has a error, else it will give error equal to 0 if there is no error. Please try to understand. If you are not understanding, ask me again, I will explain this fundamental thing. Do you all understand what it happened? It may be wire or wireless. This media may be wire or wireless. This more you can understand in the communication classes, students, don't worry. This is the basic scenario. What is happening in actually in the parity generator, it generates the parity bit which actually happened in the transmitter section. Along with the n bit message data, this parity bit has been achieved at the receiver section, and in the error detecting circuit at the receiver section, it actually processes this n bit data with parity bit, and finally if the data has an error, it provides as a e equal to 1. If it has no error, it provides error equal to 0. That too, it has only detected 1 bit error. If it is having more bits error, then it is not going to detect the thing. So do you all understand the fundamental concept here? The fundamental concept is, in the transmitter section, we have to design a parity generator circuit. In the receiver section, we have to design a error detecting circuit. Okay, the two types of circuit we are going to design now. Okay, any doubt? Or tell me if there is doubt, please let me know. So our thing is we are going to design two circuits. One is parity generator circuit. Okay, I'm going to tell all this about parity, what is parity, all these things. Don't worry. Just you need to know the objective. What is objective? We have to design two circuits. One is that parity generator circuit or parity detector or error checker or parity checker, anything. Lot of names are there for it. Parity checker circuit. Okay. Do you all understand now? The thing is, what is parity? So please understand this, very important. Parity is nothing else, number of ones in a given data. Okay, parity means number of ones in a given data. If it is, there are two types of parity. So one is even parity bit, even parity bit. We can also say EPB. Okay, and another one is odd parity bit. If you are not understanding, please unmute and ask me, student. Very important concept I am telling today. OPB. Okay, EPB and OPB. So what is now the concept is what is even parity bit and what is OPB. Even parity bit is nothing else. In order to find out even parity bit, the total number of ones including parity bit. So the total number of ones including parity bit, please understand, this is very important, including parity bit must be even. Okay, the total number of ones including parity bit must be even. Let's say I'm going to give example. What is example? Let's say my message signal is 1011. 1011 is my message signal. So this is my message signal, or you can say the like data which need to be communicated to the receiver. So this is my message signal. So what would be my EPB, even parity bit? The parity bit would be, for even parity bit, the including the message signal, including the parity bit. So this is my parity bit, EPB. Including the parity bit, it should be even. So 1011, how many ones are there? 3 ones are there. Here 3 ones are there. So this is odd. So in order to make the even parity bit, you would have 1 here. So now you can say total number of ones are how many? 4. So this is a even parity bit. Understand? Now take another example. Please try to understand, students. Very important things I am discussing. 1001. So this is, let's say, message signal. In this, how many ones are there? 2 ones are there. So what would be my even parity bit? 0. Understand? So next 1100. Here how many ones are there? 2. So what would be my parity bit? 0. So okay. So what do you understand? The total number of ones including parity bit must be even. Then it's called a even parity bit. Okay. Now we come to the odd parity bit. So odd parity bit is what? In order to find out the odd parity bit, the total number of ones including the total number of ones including the parity bit must be odd. Okay, so example, very simple. Let's say 1011 is the message signal. So here in parity bits, sorry, ones how many? 3. So what would be my odd OPB? Odd parity bit would be 0 because already 3 is an odd. Okay, next go for 1100. So how many bits are here? How many ones? 2. It's the even number. So in order to make the odd, you have to make a 1 here. So do you all understand? This is my OPB. Any doubt? Please let me know, students. Any doubt till now? So if there is no doubt, we'll move to the next part, the parity generator circuit. Okay. So the first circuit we are going to design a parity generator. So where it will be required actually at the transmitter section, the parity generator circuit. Okay, so there will be two type of circuit you need to design. One is actually even parity generator circuit as well as odd parity generator circuit. So you will be having even parity generator circuit and odd parity generator circuit. Okay, do you all understand? So how the question will come mainly in the exams? The question will come: design a 3-bit even parity generator circuit. Okay, so this would be your question: design a 3-bit even parity generator circuit. So first of all, I have told you what is actually. So you need to design a 3-bit even parity generator circuit. So obviously, what would be your 3-bit even parity generator circuit? What would be your message signal? How many bit will be your message signal? Obviously 3 bits. So what you have to do? You have to design a combination logic circuit which is actually having 3 binary bits. Okay, next it generates what? Even parity, E P B. Do you all understand, students, or any doubt? So this will be your circuit: 3-bit even parity generator circuit. You need to design here which generates a even parity bit. Okay, it generates a even parity bit. So how, what are my outputs? Let's say my inputs are X, Y, and Z. So X, Y, Z are my inputs. For these X, Y, Z inputs, I would be generating a even parity bit. Okay, then finally I will set this in the transmitter section. Okay, do you all understand or any doubt? Please tell me. So now truth table. So what you have to do here, very simple. It has 3 inputs: X, Y, and Z, and a even parity bit is a output. Okay, any doubt on this till now? Please let me know, students. Any doubt? Anybody can unmute and say me if there is any doubt. Okay, so this is 3 inputs, 2 to the 3, 8 combinations possible. So obviously 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and finally your 1 1 1. Okay, so you can see even parity bit. Already I have told you what you have to do. Even parity bit means, in order to generate the even parity bit, the number of ones including the parity bit. So this is your parity bit P. Am I correct? This is your parity bit. You have to design that. So what you need to do here? You need to find out the number of ones including this parity bit should be even. Okay. So here already 0 is a even number. So obviously we would have EPB 0. So 0 0 1. How many ones are there in this? 1. So 1 is odd. In order to make it even, I'll put EPB 1. Okay. 0 1 0. How many ones are there? Odd number of ones, only 1. So I know to make it even, I have to put 1. 0 1 1. How many bits are there? How many ones are there? 2. 2 are even, so we need to put 0. 1 0 0 odd means I have to put 1. 1 0 1 even, I need to put 0. 1 1 0 even, I need to put 0. 1 1 1 odd, I need to put 1. Okay, all of you understand how I have done the output? So finally what I need to do? I will have a logic expression. So logic expression, for that what I need to do? I would find out the minterm. So this is my minterm 0, minterm 1, minterm 2, minterm 3, minterm 4, 5, 6, and 7. Okay. So what we have got here, my EPB, we have got EPB is nothing else summation of M. What are those? 1, 2, 4, 7. Okay, any doubt on this? So we have got it like 1 2 4 7. Then we can use either K-map or using the Boolean algebra. We can simplify the logic expression, because at the end we are going to design a simplified version of logic expression. Okay, so for this we would have actually it's a 3 inputs. So X Y Z. So this will be Y bar Z bar, Y bar Z, YZ bar, because this is gray coding technique. X bar X, and what are the minterm positions? 0 1 2 3 4 5 6 and 7. Now what I need to do here, 1 is present, I'll put 1, 2 is present, 4 is present, and 7 is present. Other places it's 0. So how to combine it? I just has to combine it using single combinations. Am I correct? Okay, so for this, what we have got EPB, we have got EPB as X bar, Y bar, Z, yes, X bar, Y bar, Z plus X bar, Y, Z bar plus X, Y bar, Z bar, X, Y, Z. Okay, am I correct? So from this two, I can take a common as X bar, which gives me Y bar, Z, Y, Z bar. Here X I can take Y bar, Z bar, Y, Z. Okay. So next, this I can write down as a Y XOR Z. This I can write down as a Y X nor Z. Okay. So I can also write down this as a X bar Y XOR Z or X Y X nor Z bar. Okay. So I have already discussed with you what in the morning what we have discussed, a basic fundamental thing. What I have told to you, X sorry, A XOR B is equal to A XOR B complement. Okay, so which can also be written as what I have discussed earlier. A XOR B is A X nor B complement. Why? Because inputs here, number of input is even. If number of input is even, it would be complement. If number of input is odd, it would be same. Okay, so this is number of input is odd. So this is very important concept, student. During GATE exams, PSUs and all, this is required to you. Okay, so according to this what we have discussed, if we can take this will be, let's say X is A, so we can say this as a X XOR Y XOR Z. So we got EPB is a 3 input XOR circuit. Okay, then finally I can design it or implement it, the logic design. How to implement the logic design? Very simple. So always remember, try to design it with the help of minimum number of gates. Okay, so I can design it with the help of like this. Okay, but 3 input XOR is little bit costlier. Okay, so what I need to do, I need to take it as XY, and whatever output comes from this, I can take Z and perform the XOR. This is also same operation. Okay, and little bit less cost. Okay, this is the way I can design my 3-bit parity generator circuit. So this is called a 3-bit parity generator circuit. Do you all understand, so, or any doubt? 3-bit even parity generator circuit. Okay, any doubt on this? If not, I will proceed next. So if now the question is, let's say you have to do this at home. Design a 4-bit even parity generator circuit. So you do this at your home. Generator circuit. I am not going to do this because we have to cover many things. Okay, so I am going to design another circuit today. So it's a little bit odd parity generator circuit. Let's say question is, design a 3-bit odd parity generator circuit. Okay, so for this case what you need to do, you need to design a odd parity generator circuit. So you're obviously you would be requiring OPB, odd parity bit, and the message signal is 3-bit. Okay, so this is X, Y and Z. Okay, do you all understand? So you need to design a 3-bit odd parity generator circuit. Okay, this you need to design. So how? Please check here. So obviously we need to construct a truth table now. So what is my odd parity bit generator circuit tells? Odd parity bit generator circuit tells that in order to find out the odd parity bit, the number of ones including the parity bit must be odd. So according to that, I am going to design it. So this is my X, Y and Z, and this is my OPB, odd parity bit. Okay, so this is obviously 3 inputs. So we have actually 8 combinations. What are those combinations? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so then odd parity bit would be having odd number of ones should be there, including the parity bit. So obviously 000 is an even number. 0 is a even. Do you all know that 0 is a even number? So in order to make it odd, we need to put 1. Okay. Now 001, it's already odd, so we don't need to put 1. 0. This is already odd. 0. Next, this is even, so in order to make it odd, we have to put 1. This is odd, we need not to put 1. This is even, we need to put 1. Even, 1, odd. Okay. So do you all understand now what you need to do? Very simple, same thing, M0, M1, M2, M3, M4, M5, M6 and M7. Okay. So we have got OPB, logical expression. Next step is logic expression. Find out all the outputs logic expression, which is OPB, summation of M. What are the things are there? M0, 0, 3, 5, 6. 0, 3, 5, 6. Okay. Any doubt on this? 0, 3, 5 and 6. So next, you need to use either K-map or you need to use either Boolean algebra to minimize this, to get the minimized version of the output. Okay, logic expression. So for this we need a 3 input. So it's a 3 input, 3 variable K-map x, y, z. So this is my y bar, z bar, y bar, z, y, z bar, and this is my x bar and x. So for this, what you need to do? 0, 1, 2, 3 are my minterm positions, 4, 5, 6 and 7. Where are the positions present? 0 is present 1, 3, 5 and 6. Other places it's 0. Okay. Now you start combining. In order to combine, it's all are single combinations, because these are all comes in a diagonal pairs. So we cannot combine in diagonal pairs. We have to combine either with the adjacent cells only. Okay. So for that, what we have got? OPB, we have got it as x bar, y bar, z bar, x bar, y, z, x, y bar, z, x, y, z bar. Okay. We have got it like this. So in order to do this, what we can take common in this x bar, which gives us y bar, z bar plus y, z. Next, we can take as x common, y bar, z, y, z bar. So this will give me x bar. This I can write down as a y x nor z, and this will be x, y x or z. Am I correct? Very simple. So can I write down this way x bar y x nor z? Can I write down y x or z complement? Yes. Why? Because y and z two inputs. If it is even number of inputs, what I have told, it would be complement. Okay. So next, x, y, x or z. So what we have got here mainly? We have got here, let's say this x is a, let x is a, y, x or z is b. So this got as a bar, b bar, a b. So this I can write down as a x or b. Am I correct? Or I can write out as a x or b bar. Am I correct? So finally, what I am going to write? X, x or y, x or z whole bar. Okay. Any doubt on this? So finally, we have got logic expression for OPB, which is okay. Do you all understand? Now what we have to do? Logic design. We have to do logic design. Sixth step is you know to do logic design. So for that, what we need to do? We can have a OPB like this. It's a 3 input x nor. So this is x, y, and z. So this is my OPB. Okay, and we'll be also having like this. You can put one NOT gate also like this. Your wish. Okay. So any of this is correct. Okay. So next to homework, you need to do at home this one. Design a 4-bit odd parity generator circuit. Design a 4-bit odd parity generator circuit. This you have to do. So total 5 homeworks I have given students. Please do it. Don't neglect. If you neglect, you will not be understand better. Okay. So 5 things I have told you. Okay. You need to do those. First one is full ladder using NOR gate only. Next I have told you full subtractor using NAND gate. Next to full substrator using NOR gate, and fourth one is design a 4-bit even parity generator circuit, and fifth one is design a 4-bit odd parity generator circuit. These are the things you need to do. Okay. So next part. So in the transmitter section, what we have, we will be having a parity generator circuit. Now including the parity bit, either in the wireless media or with the help of wide media, we are going to send to the receiver section. Okay. In the receiver section, what they have received, they will receive a parity bit along with the message signal. How many bit a message signal? N bit message signal. It depends on the number of bits a transmitter section want to send. Okay. Along with that, one parity bit they will send to the receiver section. Now in the receiver section, you would be having a parity checker circuit or parity detector circuit, or maybe a error detecting circuit. Okay, if these circuits will be present, then you can tell that, yeah, the message signal which they have got is a erroneous one, or it's not having any error. So we have to design a circuit at the receiver section which can detect the error, but make sure that, remember that only one drawback here, if there is only 1-bit error, then it will be going to detect. If there is more bit error, this circuit has a drawback. How to detect that? We have different things, some Hamming codes and all. I will discuss those things in the unit 5. Don't worry. Okay. For this class, it's actually a 1-bit error circuit correction and detection. Okay. Do you all understand, students? So next part is at the receiver section, we will be having parity detector circuit. So this is another important question. What this parity detector circuit will do? It just detect a 1-bit error. Either it will tell that error is 1 or error is 0. If E output, which is error, is 1, so what it will do? It will just generate a single bit error. Okay. So this is my error bit, E. I'm going to design a circuit which gives as a E. So what it will do? It will be n-bit data. So n-bit data will come, along with that a parity bit. So this is my parity bit, and along with that n-bit data. Okay, this error parity detector circuit will detect and tells whether the obtained message signal is erroneous or not having any error. Do you all understand, or any doubt? Do you all understand what is the combination logic circuit? First step, you need to understand the problem clearly. If you understand the problem clearly enough, you can able to design the circuit, any type of logic circuit in the world. Okay. So this is my circuit I am going to design, which is actually a parity detector circuit. Okay. It actually tells the containing message signal is having error or not. It actually provides either 1 or 0, because the output is a single bit output. If error is 1, then I can say that the message signal is an erroneous one. If error is 0, I can say that there is no error in the message signal. Whatever the message signal we have got is a correct. Okay. But only one drawback, it only detects the 1-bit error. Okay. For more bit errors, we'll see later on. Don't worry. Okay. Do you all understand what you need to do? Okay. So now the question, how the question will come in the exam. Okay. So the question is design, please try to understand, an even parity detector circuit of 3-bit data. So the question may come like this, or the question also may come like this. So they may modify the question like this, or design a 4-bit even parity detector. Do you all understand, student? So I have told you two things here. You have to design a even parity detector circuit for 3-bit data, or directly design a 4-bit even parity detector. Both are same. Why? Here 3-bit data is a message signal along with a even parity bit. So total how many bit? 4-bit. Obviously they may give like this question, or they may give directly this question. Design a 4-bit even parity detector. Understand? So what would be your requirement? You will be required to design a 4-bit even parity detector circuit. Okay, you will be design a 4-bit even parity detector circuit which takes 3-bit message signal, nothing else, X, Y, and Z, along with a parity bit. You all understand? So this is my parity bit. Okay, and these are my message signal, message or data. And finally, what it will give? It will give a error. Either the detecting message signal is having error or not. So what it will generate? It will generate a EPB, even parity. Am I correct? Because I am going to design a even parity detector. I am going to design a even parity detector. So what it will do, students? Please try to understand now. So parity detector circuits gives error information E equal to 1. The input value is not in the proper parity for even parity detector. What do you understand from it? If input is an odd parity, then the error is 1. So what do you understand, students? Please let me know. If including this parity bit, number of ones are odd, then it will give error equal to 1. Any doubt? Please let me know. What it will be given? How error equal to 1 it will come? If input is an odd parity, then the error equal to 1. Okay, and if the input is an even parity, and if the input is an even parity, then error is 0. Why? So these are the two cases it will check, and it will provide either 1 or 0. Do you all understand what it will be? It will check including the parity bit. This is called parity. Input including this message signal and the parity bit. If it is having odd number of parity, then error equal to 1, because we are generating a even parity detector. Okay, if the input is an even parity, means the even number of ones here including the parity bit is even, then it generates a error 0. Why? Because we are generating a even parity detector circuit. Now do you all understand? So if next thing is, you need to design the truth table or construct the truth table. So how we check here? If you are not understanding, please ask me, student. So if you see the truth table, you will understand. Don't worry. X, Y, Z is my message signal, including parity bit is my input. Okay. So there are 4 inputs. Obviously, I can actually expect how many combinations? 16 possible combinations possible. Okay. X, Y, Z, P. So what it will tell? It will tell the error. Either error is 1 or 0. Okay. So see here what I am going to do here. 0, 0, 0, 0. How many combinations? 16. 0, 0, 0, 1. 0, 0, 1, 0. 0, 0, 1 more. So 4, 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. 8, 1, triple 0. 1, 0, 0, 1. 1, 0, 1, 0. 1, 1. No. Yes. Okay. 1, 0, 1, 0, 1, 0, 0, 1, triple 0. 1, 0, 0, 1. 0, 0, 1, 0, 1. Okay. Next. 1, 1, 0. 1, 1, 1, 1, 0. 1, 1. I have missed one thing here, I think. Yes, 1011. Okay, you guys are not telling me this is 1100. Hmm? 1100, 1101, 1110. Okay, next last one is 1111. So 16 combinations possible. Okay, do you all understand or any doubt, students? Please let me know. So these are the 16 combinations possible with this. Now it will give us what? Error. What it will give? I have told you here, if input is an odd parity, then the error is 1. Now see here, 0, 0, 0, 0, including parity bit. How many ones are there? 0 ones. 0 is a what? Even number. Even number means obviously error is not there. Okay. If it is even, error won't come. Okay. Because we have even parity detector circuit. If even number of ones detects here, it will not provide me any error. If odd number of one detects along with the parity bit, there will be an error called error equal to 1. Okay. Now 0, 0, 0, 1. It's a odd. So obviously error will detect, yes, this is a odd parity. Okay. Next 0, 0, 1, 0 odd, error detects. 0, 0, 1, 1 even number of ones 2. That's why it won't detect any error. Understand, students? Very simple. Next 0, 1, 0, 0. It's a odd. So error detects. Next 0, 1, 0, 1 even, even, odd, odd, even, even, odd, even, odd, odd, even. Okay, so this is my output error. Okay, do you all understand, students, or any doubt? Please let me know. So what we have got here, error, we have got it like E equal to summation of M. So these are my M0 to M15. So we have got M1, M2, M4, M7. What else we got, students? M8. Next M 11, 13, 14. Okay, so this is my error circuit. So next, what you need to do? Fifth step, you have to simplify to get the logic expression. So what you need to do? You need to have either with the help of KMA or with the help of Boolean algebra. So we have got here, it's a 4 variable, obviously X, Y, Z and P. So we'll have a 4 variable KMF here. Okay, so 4 variable KMF required 14 number of cells. Sorry, 15 number of cells. So how it is? It looks like this. Sorry, it has 16 cells. Okay, 2 to the power 16. So this is my X, Y, Z and P, Z bar, P bar, Z bar, P, Z P, Z P bar, X bar, Y bar, X bar, Y, X Y, X Y bar. Okay, we know the minterm positions 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. These are the minterm positions. I'm going to fill those minterms where the minterm positions are present. 1, 2, 4, 7, 8, 11, 13, 14. Okay. Do you all understand? So how many combinations possible? How? All are single, single. Because all are in diagonally present, we cannot combine as a pair. So finally what we have achieved here, we have been achieved here, like my error E is nothing else, X bar, Y bar, Z bar, P plus X bar, Y bar, Z P bar plus X bar, Y, Z bar, P bar, X bar, Y, Z P. Next X, Y, Z bar, P, X, Y, Z, P bar, X, Y bar, Z bar, P bar, X, Y bar, Z, P. Okay, so these are the things we have achieved. Okay, so finally, if you solve this off, what you will get? You will get like this. If you solve this off, you will get X, Y, Z and P. So this is my error circuit. Okay, this is also an XOR gates we have got. So finally, sixth bit is you need to design the logic design. So for this logic design, what you need to do? Very simple. You need to take XYZ and P XOR gate. Okay, so this gives me error XYZ P. Okay, any doubts, friends? So this is my 4-bit parity detector circuit, or you can all 4-bit even parity detector circuit. Okay, you can also design it in this way, like 2 bits if you want, like this. This is my XY, and it comes as like this. Then Z and P, it comes as another XOR. Then it will be go to another XOR. This will give me error XYZ. This is the way. Any of this your wish. Whatever you want to do according to design. Okay. Any doubt on this, students? Please let me know. Any doubt? If there is no doubt, we'll go to the next part. So this is one of the combination logic circuit which useful for the data communication purpose. What are those circuits? Designing of parity circuit. One is parity detector, and another one is parity generator. The parity generator is using in the transmitter section, and parity detector is going to be used in the receive section. Parity detector is in the receiver section, parity generator is in the transmitter section. So don't be confused, and this is very easy. Little bit of practice required. You need to do the practice. Okay. So next part. So next part of our syllabus is different code converters. So what is code converters? There are different codes are there, like binary code, gray code. We have already studied all these things. Gray, binary to gray code converter, let's say. Second one is gray code to binary code converter. Okay. Next one is, let's say, 8421 code to XS3 code. Okay, there are various coding circuits are there. So we'll see some of these actually. BCD to 7-segment decoder. 7-segment decoder. Okay, so these are the basic code converters. We have already seen actually what are those codes, actually binary codes. I have already discussed with you weighted code, non-weighted code. Then under weighted code there will be BCD. It has certain weights in all place values, and non-weighted codes like gray code and XS3 code. These are all non-weighted codes. Okay, it doesn't have any codes like this, and we have already discussed about how to find out these weights and all. Let's say I'm going to tell you, let's say one of these code weighted codes are like BCD codes. So please try to understand little bit. I'm just revising. We have already discussed those things actually in our previous classes. So BCD is a weighted code. Okay, so what do you mean by weight? It has a 8421. So each BCD code has a weight of 8421 in the respective place positions. Okay, so I'll tell you, don't worry, we have already discussed all these things. Like some other weighted codes are 4221, 2421, 84 minus 2 minus 1. Okay, so you can see how many maximum decimal number is possible. If it is a tell me, if it is a 842 minus 2 minus 1, how many maximum decimal position value possible? So you can see 8 plus 4, 12, minus 2 minus 1. So 12 minus 2 minus 1. So this is 9. So 9 is the maximum decimal number can be possible with this particular 8421 minus 2 minus 1 coding. So we can see how we can write these actually. Let's say somebody will ask you in the example, sorry, in the question, 84 minus 2 minus 1 coding. How can be a decimal number represented in this particular coding? Okay, maybe come in 2 mark question. You will understand, student. So 84 minus 2 minus 1 coding, how can be expressed in decimal, this particular decimal numbers, how can be expressed in particular 84 minus 2 minus 1 code. First of all, you should know how, what is the maximum decimal number possible with this. So we know that 84 minus 2 minus 1, it has 9 is the maximum decimal number. So you can make a column like this, which actually have 9 up to 9 decimal number, and we need to find out the coding, particular coding in 84 minus 2 minus 1 coding technique. Okay, so it starts from decimal number 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So maximum 9. So I will not proceed further. Okay, so now tell me, so 0, how can you represent 0? 0 means all should be 0. You can see in this place values, if I put 0, all will be 0. Now decimal value 1. So decimal value 1 means, how can we represent 1? So let's say I'm going to take 4 minus 2 minus 1. So this will be 1. Am I correct? This place 0. Do you all understand? In decimal 1 can be represented as 0 triple 1 in 84 minus 2 1 minus 1 code. Do you all understand or not, students? Now how to represent 2? 2 can be represented 4 minus 2, 2. Okay, other places 0. 3 can be represented as how? 3, how would you represent 3? 1, 1. Okay, other places 0. So this will be 4 minus 1, 3. 4 can be represented as 1, 0, 0, 0. Okay, 5 can be represented as how? How 5 will be represented? 5, 8, 0, 1, 1. Yes, 5. 8 minus 3, 5. So 6 can be represented as 8 minus 2, 6. Okay, do you all understand or any doubt? 7 can be represented as 0, 0, 1. Okay, next 8 can be represented as 1, 0, 0. 9 can be represented as all ones. Do you all understand? This is the way I can design, I can represent any decimal number in 84 minus 2 minus 1 coding. Okay, any doubt on this, students? Please tell me, any doubt? So how the question will come in the exam? Okay, now the part is how the question will come in the exam. The question will come like this. So this is very important. Already it came in the 2018. Okay, so you have to design a code converter. Design a code converter which converts 3-bit binary number, 3-bit binary number to XS3 code. So what is the what actually asked in the question? Design, you have to design a code converter circuit which converts 3-bit binary number into XS3 coding. Now tell me, how many, what you have to do? This is also a combination logic circuit. What you have to do? You have to first understand the problem clearly. So what you need to do basically here, students, you need to convert a 3-bit binary number to XS3. So maximum, tell me, in 3-bit binary number, maximum bit is what? Maximum 3-bit is what? 1, 1, 1. All will be 1, then will be maximum number. So what would be the particular 3-bit number? This is 7 decimal number. So what is XS3? XS3 means what I have told you, mainly you have to do plus 3. So it would be what? 10. So in order to represent 10, how many bits are required? 4 binary bits are required, 1, 0, 1, 0. So what you will give here? You are giving input 3 bits, but how many outputs you are requiring? 4 bits. Do you all understand, student, clearly? So you will be required 3 input. So you have to design a combination logic circuit which actually a 3-bit binary number and provides a 4-bit XS3 code. Understand or any doubt? Tell me. So this is your 3-bit binary to XS3 converter circuit. You have to design this. Okay, why we require 4 outputs? That is important. Here nothing is important. So 7 is the maximum decimal number can be represented in 3-bit binary binary numbers. So what are those? 1 1 1. So in order to get the excess 3 of 7, we have to add 3, so which gives me 10. 10 can be represented in how? 1 0 1 0, 4 bits, but input is 3 bit, output is 4 bit. Do you all understand now? So what are your input bits? Input bits are your 3-bit input. So 3-bit input means it would be having B2, B1, B0, 3-bit input. And how many excess 3 bits? Outputs E3, E2, E1, E0, 4-bit output. Okay. So in order to construct this truth table, you will be having 3-bit input and 4-bit output. So obviously, what are the things we have got at input? B2, B1, B0. Next E3, E2, E1, E0. Any doubt on this? You have to design a 3-bit binary to XS3 code converter circuit, which converts a 3-bit binary number to the corresponding XS3 coding. Okay. Many of the students, they will make mistake. They will make 3 input and 3 output. Okay. So please be understand the question before going to solve it. Okay. That's why first step of design is actually you have to understand the problem clearly. Okay. So obviously 3 input means how many combinations possible? 2 to the 3, 8 combinations possible. So what are those? 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Any doubt? Simple. So this is 3 0 0 0. 0 0 means 0 means what is decimal equivalent? Decimal equivalent of 0 is 0 0 0 0. This is 1. This is 2, 3, 4, 5, 6, 7. Now tell me 0 excess 3 of 0 is 3. 3 means how to return 3? 0 0 1 1. Simple. Okay. Next 1. What is excess 3? 4. 4 can be written as 0 1 0 0. 2. Decimal 2 means excess 3 is 5. 5 can be written as 1 0 1. Simple. 3. Excess 3 is 6. 0 1 1 0. 7. You will get 7 next. 4 excess 3 is 7. 0 1 1 1. Okay. Any doubt on this till now? Next. Do you all understand or any doubt? Tell me. Don't be get confused. Just you need to find out excess 3. 5. What is excess 3? 8. 8 means 1 0 0. 6. 6 plus 3, 9. 9 means 1 0 0 1. 7 means 10. 1 0 1 0. Simple. You got the inputs, you got the outputs. Now tell me what you have to do next step. Next step is you need to find the logical expressions of all the outputs. So how many outputs are there, students? Here outputs are how many? E3, E2, E1, E0. 4 outputs. So you have to get 4 logic expressions. Okay. So what are those logic expressions you need to find out? You need to find out for E3 some logic expression, for E2 some logic expression, for E1 some logic expression, for E0 some logic expression. Then finally you need to design. So for E3, what are the summation of M0 min terms? 5 6 7. So for E3, summation of M 5 6 7 for E3. Okay. Next for E2, summation of M what? E2 1 2 3 4. 1 2 3 4. Summation of M 1 2 3 4. For E1 0 3 4 7. 0 3 4 7. Summation of M 0 3 4 7. Next E0, E0 is 0 2 4 6. 0 2 4 6. 0 2 4 6. Do you all understand? Now what you need to do? You need to find out the logic expression. So for E3, what you need to do? You have to solve the K-map. So it's a 3 variable K-map. What are those 3 variables? B2, B1, B0. The inputs are what? B2, B1 and B0 are my inputs. So my K-map is actually B2, B1, B0. So this is B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Next B2 bar, B2. Okay. So you need to put those for E3 567. So 567 is mainly here, 567. Other places are 0. So how to group it? Very simple. You can group it like this. Okay, this gives you B2 B0. This gives you B2 B1. So finally you have got it like E3, which is B2 B0 plus B2 B1. So I can write down it like this also, B0 or B1. Okay, do you all understand? This is my E3. Similarly, you can do for E2. E2 again one more KMF, 3 variable KMF. Okay. Okay. So this is my B2, B1, B0, B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. This is my B2 bar, B2. Okay. So here how it is like 1, 2, 3, 4. 1, 2, 3, 4. Okay. So other places it's 0. Very simple. So you need to do it like this one more combinations, and this will be single. So this you got E2 as B2 B1 bar B0 bar, next to B2 bar B0, next to B2 bar B1. Okay, this is the way you need to do. So you can also make it like this: B2 B1 bar B0 bar plus B2 bar common you can take, and this B0 or B1. Okay, so this is my E2. Similarly, you can design it for E1. So again, it's a 3 variable KMF. So for this, again, you would be having B2 B1 bar B1 B0. So this will be B1 bar B0 bar B1 bar B0 B1 B0 B1 B0 bar. Okay, so this will be B2 bar B2. Okay, so for this E1, what are my E1? 0347. So 0347. So how to group it? This is one more grouping, this is another grouping. Here you got at E1 is B1 bar B0 bar, and here B1 B0. I can make it like this also, B1 X nor B0. Okay, next last one is E0. This is again a 3 variable KMF. So I can construct a 3 variable KMF like this. So this will be your B2 B1 B0, B1 bar B0 bar, B1 bar B0, B1 B0, B1 B0 bar, and this is your B2 bar B2. Okay, so this will be E0 is what? 0246, 0246. So for this 0246. Okay, so I can make it like a single grouping of quad like this. Okay, so what I got here, E0 is B0 bar. Okay, so finally what are the equations we got? So how to design? The last step is the logic design. Okay, so for the logic design, what I have told you, you would be having B2 B1 B0. So also it would be having B2 bar B1 bar B0 bar. Okay, so now you can do the logic design very easy way. Okay, so this will be your B2 B1 B0 inputs. Okay, so what is my E3? E3 is B2 and B0 or B1. B0 or B1. So this is my B0 or B1. B0 or B1 with end operation with B2. End operation with B2. So this gives me the E3. Similarly, what is E2? My E2 is B2 B1 bar B0 bar. B1 bar B0 bar B2. Okay, B2 B1 bar B0 bar. Okay, this will be one AND gate. Next, B2 bar B0 or B1. B0 or B1. So this is my B0 or B1 B2. B2 or B2 bar. B2 bar means here. You can just, so this is my B2 bar, B0 bar, B1. Okay, and finally you make the end of or operation. So this will give me E2. Okay, any doubt on this? B2 bar, B0 or B1. So this is actually, I made a small mistake here. This will be or, this will be and. Okay, so this will be or, this will be and finally next E1 is B1 XOR B XNOR B0. This is B1 XNOR B0. Okay, so this is E1 and finally E0 is nothing else my B0 bar. So this is my B0 bar, which is E0. Understand, students? Very simple. I have just designed the circuit as per the logic diagram. So this will give me the circuit code converter circuit, which converts a 3-bit binary to the XS3 code. Okay, binary to XS3 code. Okay, so do you all understand or any doubt, students? Please let me know. Any doubt?